Bismillahirrahmanirrahim. Assalamualaikum. Good afternoon to all. This is the next lecture on neural network. On the part 2A, we have broken up into two. One is the 2A on modeling, and the 2B will be on the control side. Okay, these are the basic steps we have to follow when we want to do system identification or modeling using neural network. If you've seen before, the neural network is in terms mainly of the structures of the neural network topology. We call it neural network topology, the structures in terms of nodes, number of nodes, the layers, and so on. So these steps is the basic steps that we need to follow. We really want to get a good, robust neural network. These are the steps that we need to follow. Basically, the model structure and size, the data set, compilation, input excitation, input output data, the weight initialization, the methodology, and model validation. Of course, in the software, we can just choose anything we want, but if we do it blindly, we're not going to get a good system identification or modeling using the neural network. It will not be robust. It may work for that case, but for the other case, it may not work. So we follow these steps strictly, we will get a good, robust neural network that will be available or applicable for all different scenarios for the process system. Okay, it's on the model structure. There's no standard method to determine the structure and the number of nodes. If there is, we would have been using it. There are different ways of doing it and so on. But what normally we do is we fix an initial size of the hidden node, and then we will, after we have fixed it, then we will go through the normal training program, training and so on, until satisfy the error requirement. Once it satisfies the error requirement, then we can basically consider it as the network that we want. If it does not satisfy, then we have to go again, and we have to start using another set of topology and keep on repeating the steps that we'll show later. So mainly, although the choice is done by trial and error, normally after a few trials you do it, you will get an optimum range about the number of nodes that we need. Mainly for the middle nodes, because the input and output is fixed by the system that we are going to model. But this is mainly for the hidden nodes, to decide how many hidden nodes we need, or maybe how many hidden layers we need. Okay, what are the transfer functions that we need? What are the what you call the activation function that we need to use for that system in hand. That's the first part, the main model structure and size, basically the topology of the system. The second is to get the data sets for us to train the network. Training means basically to optimize the network, so that we mainly optimize the weights. Once we get the optimized weight with the topology, that is the network that we want. Okay, so we can get data from model simulation, which in this class we will get from simulation, or if we have online data, or we can combine both of them. And in utilizing the neural network, the two data sets at least are required. One is for training and one is for validation. Okay. Sometimes we have what we call the train set and also the test set before we validate. So sometimes we have two, but sometimes we just call training set, sometimes called test set. Depends on different scenarios. So basically the training set is where you use to train the weight, and you test it with another set to get the generalization capability of the network. Okay, once we are satisfied, we can go back and forth. Then we use the validation set, which is the data set which is not seen by the network. It's new, not seen by the network. So once the validation is okay, means the network understands the system. Okay, whether it's a steady state or dynamic, it's up to us to come up with the data set. We want a steady state modeling, we have to have the steady state data set. We have the dynamic modeling, we have to have the dynamic data set together with the steady state data set as well, normally, because the dynamic system is basically, or the steady state system is basically the special case of the dynamic system when things are not changing. Okay, then how to incite the input for the data. what types of input signals we want to use, what is the frequency, what is the magnitude. This we have to also choose it properly, especially for dynamic system, especially when it's non-linear. We need to make sure that the data set is represented that we are trying to model or identify. So normally we can use the input step, pseudo random binary, or the RAM sequence and so on. But when we have a non-linear system, we may not have just binary, but we have different magnitude for the input data, so that it gives you a complete range of how the output is going to behave. Binary may not be sufficient. It may be sufficient for linear system, but for non-linear system, binary data may not be good enough to represent the behavior of the system. Then we have to decide the input-output data. Okay, of course we have to decide what is the input or the output based on the process that we are looking for. If we have to decide what is the input we need to for the know what is the output that we're trying to map, and then we have to come up with the data. If we want a steady state, then we have to choose a steady state behavior for the system. Okay, the choice of input depends on the relevant variable likely to affect on output. So we should also do some simulation before that uh, to check which inputs have the main effect on the system. Not everything we're going to go into inputs to the neural network. What are the main inputs? That's the decision for the input output. And then we have to decide how we want to model the data, steady state or dynamic. And again, for dynamic, the choice of the inputs, again, important, what we're going to put into the network, and the relevant time of history for the input and output. Dynamic depends on the time data in terms of basic time lag. The past data have effect on the future data. So we have to take the past data, not just put the time. The time itself, sometimes people just put 2 time represent dynamic. That's not so good. It's the set of data before. If you want future, many types of future, the set of data after that will affect the modeling. Okay, so the knowledge of the system is used as initial guide. To decide how much past data we need, we look at the model of the system, the discrete time model. And also it has to be scale between the lower and upper bound. Okay, all these data have to be scaled, of course, because if you do not scale it, then you will not get a relevant uh, effect on the output. If the input data is very big, but the other data is small, that input, the big data, the big numbers will influence the system, whereas it may not be really true. It's just the values are big with the volume or something which is big, but the concentration is small, but the concentration may just be as important as the volume and other things. So you have to scale them to get a good feeling of how the system really works. So this is, then we have to initialize the weight, of course. This is normally done by the software, but we have to normally make it random. Yeah, between -5 to 5, not necessary. And random, not the same. If it's the same, then the effect on the network change will be very small. So that also the output response change slightly different every stage. Okay, you don't have a symmetrical pattern. If you keep the same, then everything will be changed similarly, and the effect on the next step will be good, and also promotes faster convergence. Depending on what type method you use. Then the training methodology. Okay, different networks requires different training algorithm. We have been using what we did before, the backpropagation I taught you last week. Last week, the first lecture on neural network. We have been told about this backpropagation. So the objective of training is to acquire the optimal weight for every connection in the network. As we said, the main part of the neural network is to get the optimal connection weights. That's basically the optimization. We call it training. Okay, we can use very different types of training algorithm. Less training time, but more complicated computational uh, complexity. But if you use a simple method, backpropagation is a simple method, conventional, simple, takes longer time but less computational, basically burden on the computational load. And finally, of course, you need to validate. Once you train and test, you need to validate it. based on the data that have not been seen before, and then you can use other some different equations to find the actual validation error. You can use the RMSEA, root mean squared. Okay, you can use others to also to decide on the value. You can all this together, not necessarily one. So why we need to validate is to measure how well a model fits on the data that has been trained. Of course, it will fit very well because you have trained it, you optimize it until you get the best. So it's no point to validate with the same data. You have to validate with other data that's not seen before. If it's good, means it has understood generally the behavior of the system. And also we can penalize by using some of these criteria. We can penalize the model if you have too many parameters, too many nodes. Then it may be giving a good error, but it's not good data, not a good model. It's too many parameters. So we can try to get a balance between medium parameter set and also good error set. So then we can use some of these criteria to include the model topology inside the error criteria. But it's not necessary if you are very confident about your neural network, knowing that this topology is the best, give the best smallest error. Whatever you do later also will not affect. So that's depend on how you decide. This is basically the step that we need to follow. We follow this closely, then we're going to get a very good robust neural network. As I said before, first you get data, you generate the data for training and validation with the suitable input-output signal. Decide what are the inputs, output data that you need to set into the network. So there can be many types, many inputs, many outputs. And you have to scale them accordingly. Normally -1 to 1 or 0 to 1. Then you set the suitable network configuration. You have already fixed the input how much you want, the output how many nodes you want. So you just have to first start with the initial guess for the middle nodes, and then initialize the weight and start going through the neural network process. Use all the data set you have, and finally find the final error. Okay, if the error is small, then validate with the non-seen data, it's not seen before. If it's okay, then validation is satisfactory, the neural network is okay. If it's still not okay, the validation does not work. Training and test works, but validation. So you have to do two things. Sometimes we initialize the weight, okay, but since you have randomized, not so big issue. And then the most important, we configure the network, change the number of nodes again. Okay, if the already big nodes, change the number of layers. Possible to change the number of the activation function that you use. Okay, all those different topology changes can be done here, and go back until you get the error criteria that you want, which satisfies the validation. Okay, the input output basically has already been finalized. What is the input? What is the output? You should not be changing what is the one that you put as input variables and what is the one that you need to predict. That one you should already decide what you want. Okay, unless you later on you want to use another network to predict another output, there's another issue, another network. But this has already been fixed. Normally, it's good to just have one output to predict one variable. If you want to predict another variable, you use another neural network structure, because that seems to be most stable network is when you have only one output. If many outputs, sometimes the neural network become unstable. Okay, so these are basic steps you follow until you get the final neural network structure. This is the same step that we use normally for identification also. If not neural network, other methods of identification, nonlinear regression method, polynomial regression, we use the same structure basically. Only thing we do not have the in terms of nodes, but we have in terms of equations. But the steps are normally the same for system identification for any method that you may use. Okay, so under identification or modeling refers to the same thing. Identification may mean not necessarily the overall model, may mean the parameters itself. The model means the overall behavior of the system. So we have two. One is the steady state or dynamic state modeling. Okay, for the steady state, basically what we want is to just predict the steady state behavior. Okay, in this case we have this reactor here, a batch reactor but we want to predict only the steady state model. So basically we choice of input to the network depends on the relevant variable likely to affect the output prediction. Okay, choose the relevant variable to affect the output prediction. Then these are the equations that we have. So basically what we need is now to find the model to predict the output with respect to the input. So what are the inputs? The inputs are the input concentration for CA, BO, CO, and also the time, also the space time, okay, or the time constant of this reactor here. Okay, and then the output is the output concentration of CA, CB, and CC. So this is what the model tells us. So we know what is the output, what is the input, and also the space time that have an effect on this reactor. Okay, which is basically in this case is the whole time, holding time. When some constant holding time, space time may mean the same thing for some systems, especially steady state, but for others it may not mean the same thing. So we have to look what we're looking for. But because this is an important variable in the equation, so definitely we put this an input. Okay, there are other variables here like K1, K2, which are constants, so they're not really something to be put as variable. So we do not put it. Okay, so if in the neural network, we have decided the 4 inputs, CA, CB0, CC0, and the tau. Okay, since they are steady state, so they're not time based. Just one value at one time at that steady state time. And these are the outputs, 3 outputs. So 4 inputs, 3 outputs for the neural network structure. So how to model the neural network? We basically prepare this different steady state data set. We call it the train and testing set. By changing the inputs to get the different outputs. So there's one set, another different input, another output. So those are the different sets of data we need to train based on this steady state data set. Many data, not only one specific condition, but many data sets to make the model understand the behavior of the system at the steady state point. And then validate it with the unseen data set, which means those values that you have not given it for training, validate it once. Okay, you have one set of data once. You have 2 sets of validate, another set of data to validate. It's up to you how many sets of data you want to use for validation. If you feel 2 is not enough, then try another set of data for validation. Okay, and then finally we have the once the data set for validation is okay, you reach the error criteria, then you can say that the model is what we want, and this is the steady state model using the network steady state model for that. So in this case, we have just now 4 inputs or 4 nodes, 3 output, 3 nodes, and this is from the trial and error. After you try, start maybe from 4, go to, if it doesn't work, change to 5, and so on. Then go to 6. Okay, doesn't mean the more nodes in the nodes better error. No, not necessary. There may be an optimum. In this case, maybe 5 nodes. So finally, the 5 nodes is accepted. Okay, and initialization normally use random. What type of network? The feed-forward multi-layer fully connected. Every node is connected to one another. The training method we use, the backpropagation data set, we use a steady state. And what is the error we use to stop at the end of training? 0.001. Okay, so that when we reach this, we say, okay, stop training, and then we validate it. Okay, and then that's it. The topology other than that is the activation function lah, which normally we have the sigmoidal or the linear in the input layer and the output layer. Okay, that one we may also have to specify in our specification. And for the dynamic steady state modeling, we have the same thing, input and output structure, but the only thing is now, since it's dynamic, so we need to have the time lag data. So the input with past data, one past data and many more, 1, 2, 3 until the end past data for the input as well as for the output past data, because the input past data and the output past data has an effect on the prediction in the next step. That's a dynamic system. So we have to input the time lag for U inputs and time lag for Y. There are many inputs and there are many time lag for Y's. for use, and also for wise. But normally, as I said, normally to be stable, you normally use only one output. If you want another output to be model, we use another set of neural network data, neural network model. So this is how we go. This is the actual model output, compare with the neural network prediction, and then check the error. If the error is still high, then keep on changing the neural network configuration, model topology, keep on changing until the error is satisfied. Then we stop this training process. So this is how we do it in training. Based on the identification steps just now that we showed, this is how the block diagram of how we're going to do for training the neural network, whether it be steady state or the dynamic model. This is dynamic because you have time lag, and also you have the structure this way. For this, for dynamic steady state model, we call it the forward model. It's a model actually, but forward because we can also have inverse model. So to differentiate between forward and inverse, this we call the forward modeling. But when we talk about just model or system, it's normally the forward. And if you want to predict many future values, yk at this point, yk in the next step, and the third step, for normally for optimization purposes, we can do it, do the same as before. The input values plus its lag time, the input value at the time plus its lag time, the output values plus its lag values just before. But since we want the future C2 values, then we also need to put the future CO values, which can be done if in simulation we know what is the future use that we want to use, so we can put it inside the network, and then we can get the prediction of the output for this, for the k plus 1, k plus 2, k plus 1 this time, and the future times. This is how we call it the moving window technique strategy. As we go along the data set, we will get the future data as being predicted. And for the dynamic modeling, case study of two tanks in section. It is two tanks, normal two tanks, but we have reaction versus other reaction. So it's non-interacting, perfectly mixed, isothermal. So we're just looking at the concentration, not the temperature. We can have also both temperature and concentration. We can have only temperature or both, or only one, or whatever else. It's up to us. In this case, it's isothermal. So we just consider concentration. We have this reaction going on. So this is a nonlinear system. So we are trying to use the network to predict the output based on the inputs. Okay, so the logical output will be, of course, the output coming from the tank, the second tank, C2 in that case. Okay, and the logical input will be the C0 input that's coming in, concentration coming in. Okay, so how to model? Again, as before, we prepare the dynamic data set for the training and testing. Okay, as I said, training is one. Sometimes this both are called training data, but sometimes it's called training, and then testing is a little bit generalized data, and then train and test the data based on this dynamic data set. And then we'll validate with the unseen data set. We call the validation data. If the network is fitted with the validation data with the criteria that we want, then model is optimal. If not, we go back to the changing the topology until we get what we want. So in this case, we have decided 15 inputs, 15 nodes, because we're talking about future prediction. So we have the C naught with its past data, C2 is past data, and C naught future data. Hidden layer signal is obtained from trial and error, and output layer is the prediction of C2, the output concentration at this step plus the future one, so it becomes 5 output layer. As I said just now, normally we would like to have one to make it stable, but in certain cases, if you want to have for future, you can use it to predict 5 outputs, but it's not so encouraged. If you want to have 5 output, you can have 5 data, 5 neural network. A bit more tedious, but more stable. In this case, it's stable. In many cases, it may not be so, but it's okay. It can be done. Neural network can be used to predict many output. And weight analyzation is basically randomized, and then the feed-forward multi-layer fully connected system, the back propagation training, the dynamic data set, one for training, one for testing, and one for validation, and then the error we use to end the training, 0.0017. When do we stop the training? When it reaches to this error. Well, the error initially will be very big because it's very all random weights and random topology. But as you go on training and training using backpropagation, we can see before the weights are being changed appropriately and so on. The next step. So after a few cycles, it will be 100, will be 1,000 cycles, the error should be coming down. And once it reaches the criteria we set, we stop it. And then you use the next data set, testing data set, and if it's okay, then move to the validation. That's it. So in this case, we had just now 15 inputs, which means the CO value at that time and nine values, 4 past values and 4 future values of the input. CO, we call it as the input to the neural network, and the output concentration, also the past values of the output, the present value, and the 6 past values for C2 as the input. So it becomes 15 input just now, and 5 output, because this we want to predict the concentration of C2 at the next time step and the future time step. And this is what we mean the data set. Okay, this is the training data set to train the network. So this is how we excite the input. The C0 is in this form, multi-step form. Okay, and that is C1 concentration from the first tank. C2 is the concentration from the second tank. So this is the C0 is the input. C2 is the output. C1 is the intermediate tank. Okay, we can use it as an input if we want, but it's not really necessary because C0 affects C1 and then affects C2 directly. So either go straight, the relation is C0 straight to C2. But if you want to add C1 as part of the input, it's also possible. It's possible, just more burdensome, more work, more data set, but it's okay maybe to just slightly improve the method of training. It's another set of data. We call it data. So this set, you see the different step going up, and a step going down, step up. So different shape, different what you call different values, and different style of changing the inputs. So and then you get this C1 also changing and C2 changing. So this is another set of data to train the network, testing data. So we have to train, test, and then we are satisfied with both. The error criteria for both are okay. Then we move to validation data, which is not given for training. This is a RAM data, so you're not going up down. And this is how the C2 changes. So when we give this new validation data, if the error is still small, that means the network is generalized or understood the modeling, have got a good modeling capabilities, and we can use it as a final network. Okay, so these data steps and how we generate is very important. They are very different, very varying. It shows the different aspects of this model. It shows the non-linearity. It excites the non-linearity. Then we'll have a good model neural network. If not, your neural network may not be robust. It may not be able to for many other. Then, other than that, we can also have the inverse modeling, where instead of predicting output with input, we predict the input with the output, just opposite. And this is useful for control strategies. Okay, and we'll see that in the next slide. For control, the next topic for control, we will see what the inverse modeling. But we have both. One is the forward modeling for the normal modeling process, and we have the inverse modeling for using it in the control configuration, as we will see next. Okay. Thank you very much.